Let us start. What is the activation function? Activation function defines the output of input or different set of inputs, or in other terms, it defines the node of the output node that is given in inputs. They basically decide to activate or deactivate neurons to get the desired output. This is probably the most important and single line that can explain the use of activation function in neuron. They basically decide to activate or deactivate neurons to get the desired output. It also performs a non-linear transformation on the input to get better results in a complex neural network. Activation function also helps to normalize the output of any input in range between -1 to 1. Activation functions must be efficient and it should reduce the computation time because neural networks are sometimes trained on millions of data points. So this is a typical calculation that is done in the node of a neural network. So you have your input and you multiply it with the weights of your node. So you multiplied it and you add a bias and you aggregate all this with the output of the node, that is y. Here y can be anything for a neuron between range of -infinity to +infinity. So we have to bound our output to get the desired prediction or generalized result. Then this entire thing is passed to activation function, and based on it, it will be decided whether the neuron is activated or not. So we pass that neuron to activation function to bound our output values. So this is the role of an activation function in a nutshell. Now, why do we need activation functions? Without activation functions, weight and bias would only have a linear transformation. Or neural network is just a linear regression model. You just simply are multiplying weights with the inputs and adding a bias. So that is your simple linear regression model. It is y equal to mx plus c. A linear equation is polynomial of 1 degree, which is simple to solve but limited in terms of able to solve complex problems or higher degree polynomials. But opposite to that, the addition of activation function to neural network executes the non-linear transformation to input and make it capable to solve complex problems such as language translations and image classifications. In addition to that, activation functions are differentiable, due to which they can easily implement backpropagations, optimize strategy while performing backpropagations to measure the gradient loss in the neural networks. This is why we need activation functions. So this is the structure and working of all the calculations done inside a node. So these are all your inputs. Now you calculate the multiplication of weight and input x. So this is the first input x1, this is the second input, and you are adding a bias and you multiply weights by your x input. So w1 x1, w2 x2, and you add a bias. So this entire thing is z, and this z is now passed after adding a bias is now given to activation function, and here it will decide whether the neuron is activated or not, and finally we'll get the output y. So this is how activation functions work. Now different type of activation functions that we frequently use to implement a neural network. This will be more clear to you when I show you the practical implementation of a neural network using TensorFlow and Keras, and we'll use these neural networks to solve different problems like regression and classification. So you have to know these activation functions because we'll be using them in the next few practical videos. The first and the most important one is the sigmoid or logistic activation function. The sigmoid function curves look like this. This is the mathematical equation for the sigmoid activation function, 1 upon 1 plus a to the power minus z, and this is the entire range that you can see between 0 to 1 of the output on the y-axis. The main reason why we use sigmoid function is because it exists between 0 to 1. Therefore it is specially used for models where you have to predict the probability as an output. Since probability of anything exists only in range of 0 and 1, sigmoid is the right choice. The function is differentiable. That means we can find the slope of the sigmoid curve at any 2 points. The function is monotonic, but function's derivative is not. The logistic sigmoid function can cause a neural network to get stuck at the training time. The Softmax function is more generalized logistic activation function, which is used for multi-class classification. So mostly, as a thumb rule, at the final layer of the neural network in the output node, if we are solving a binary classification problem, we'll use the sigmoid activation function. If we are solving a multi-class classification problem, then we'll use Softmax as the activation function. This is the thumb rule that you can remember. The next is tanh or hyperbolic tangent activation function. Tanh is like sigmoid but better. The range of tanh function is from -1 to 1, Tanh is also sigmoidal or S shaped. So these are the two curves. The red curve is for sigmoid and the green curve is for Tanh. The range of Tanh is slightly different. Sigmoid was existing between 0 to 1, but for Tanh we have a range of -1 to +1. The advantage is that negative inputs will be mapped strongly negative and zero inputs will be mapped near to 0 in the Tanh graph. The function is differentiable. The function is monotonic while its derivative is not monotonic. The Tanh function is mainly used for classification between two classes, again very similar to your sigmoid function. ReLU, probably the most used and popular activation function in the anti-deep learning ecosystem. The ReLU is the most used activation function in the world right now, since it is used in almost all convolutional neural networks or deep learning. So this is the graph for ReLU. You take the maximum of 0 and the value and you return it. So this is how you implement ReLU. Now the range for ReLU is 0 to infinity. As you can see from the graph, it starts from 0 and it goes till infinity. The function and its derivative both are monotonic, but the issue is that all negative values become 0 immediately, which decreases the availability of the model to fit or train from the data properly. If you see very carefully, on the left hand side, once you go below 0, everything becomes 0 in ReLU. So that is the problem, and that says that means any negative input given to ReLU activation function turns the value into 0 immediately in the graph, which in turn affects the resulting graph not by mapping but the negative values appropriately. So to solve this, we have a leaky ReLU. It is an attempt to solve the dying ReLU problem. If you see the graph very carefully, we are adding another weight. Instead of just directly f of y is y, we have f of y is equal to a of y. So this is the graph for leaky ReLU, and it is an attempt to solve the dying ReLU problem. So this leak that we have created helps to increase the range of ReLU function. Usually the value of a is 0.01 or so that the a we are adding, the value is around 0.01. So we are not making a minor change, but we are trying to solve that negative issue that was there in the ReLU. So when a is not 0.01, then it is called randomized ReLU. Therefore the range of leaky ReLU is -infinity to +infinity. Both leaky and randomized ReLU functions are monotonic in nature. Also their derivatives are monotonic in nature. So these were some of the different activation functions that we are going to use. Now ReLU function is mostly used in the hidden layers of the neural network, whether you're trying to solve a classification or a regression problem. Also in CNN, convolution neural networks that is used to work with image data, we use leaky ReLU in the hidden layers. So I hope you're clear with the different activation functions in neural networks. Thank you for watching the video. Now let's move to the next one.